Hello, hope I am audible. So in the last class we are talking about the two structures of buck converter. One is called the conventional buck converter, where you have a switch and a diode. This is the switch Q and a diode D. That is the conventional structure. And then there is one structure which is more versatile. I will tell you why it is more versatile, which has two switches, active switches Q and Q bar. So let's take an example to understand this issue. So let's take an example of a the thing that we had taken earlier. So that is a 10 volt VG. VG is equal to 10 volt. V naught is equal to 4 volt, and R is equal to 1 ohm. That kind of structure. And we have seen that I don't remember the value of the L. Can anybody tell me what was the value of L chosen for 40% ripple? It was some 10 or 15 microhenry. Exactly what was the value? We had chosen delta IL by IL is equal to 10 micro. Thank you. So that was the 10 micro. So what it implies is if I draw qualitatively the current waveform, that current waveform would be like this and coming down to this value. That is the ripple. Ripple is 40%. So we know the average value. Average value is, it has to be how much? Average value is 4 ampere. 4 ampere. And ripple is delta IL, therefore is 1.6 ampere. And this is symmetric, plus minus. So this top peak will be then 4.8 ampere. And this fellow, the bottom fellow, will be 4 minus 0.8 is equal to 3.2 ampere. So this is what will be the waveform and the numbers. Now let us say we are changing the load. We are changing the load resistance. So if I change the load resistance from R is equal to 1 ohm to R is equal to 2 ohm, what would happen? Can anybody tell what would happen if I change now R is equal to 2 ohm? How the current will change? How the current waveform will be changing? First of all, what will be the output voltage? D is equal to 0.4. Duty ratio is equal to 0.4. Therefore, the output voltage is V naught is equal to dVg. We have known that it is equal to dVg. D is equal to 0.4. Therefore, the output voltage is 4 volt. Now, what would happen? Will happen if without changing anything, to complete the information, Ts we are not changing. Ts is equal to 10 microsecond corresponding to 100 kilohertz. That is not changed. Only thing I'm changing is the load, which is a practical thing. Load can change, vary. So load is now 2 ohm, is 2 ohm. So what will be the output voltage? First, let me understand what will be the output voltage. Will the output voltage be different?
No, sir, same.
Same, yes. You have observed that the output voltage will be same. So, but the current will be same, current will be different, isn't it? Because the current is I naught is equal to V naught by R, right? Now the current has to be V naught by R, R is equal to 2 ohm. So the current average value has to be 2 ampere. So let us try to sketch it. Average value now has to shift to 2 ampere. This is 2 ampere. Will the ripple change? Question is, will the ripple change? Current ripple change? Will the current ripple change due to the change of resistance? Yes. Will the current ripple change? You can think qualitatively.
The current ripple depends on R also.
No. Where did you see? Which delta IL by IL, that expression, where is R? Vg is not changing, V naught is not changing. What is the basic expression for current ripple? Delta IL during on time. What is this? Vg minus V naught by dTs. by L into dTs. That is the current ripple, right? So what is changing in this? Vg is not changing. I said it is still 10 volt. V0 has not changed because D2 ratio is still 0.4, and L has not changed. It is a component of the circuit, and dTs is again the remaining same, unchanged. So delta IL cannot change. So even though the load resistance has changed, therefore the output current has changed. Therefore the inductor's average current has changed. Average current has changed, but the delta IL has not changed. So how it will look like the current waveform? Current waveform will look like this. So therefore what will be the peak value? 2 plus 0.8, 2.8. 2 minus 0.8 is 1.2 ampere. Right? Now,
but the ripple factor will change.
Yeah. Delta IL is not changing, factor may be changing. Okay, yes, factor will be changing because the average value is 2 ampere. So now the factor is delta IL by IL is 1.6 by 2. Earlier it was 1.6 by 4. That was delta IL by IL, right? 40%. Now it is more. It is 80%. Fine. Next, what happens? Next is I further reduce it. Let us say I reduce it to 4 ohm. Okay, so then what happens? So 4 ohm means I am now bringing down the average to 1 ampere level. I am bringing average, assuming that it is working in the similar manner. Let us say can it work in the similar manner? Yes, let us consider it. So this is 1 ampere. Correct? And the ripple, assuming that it is remaining, not assuming, actually ripple would like to remain the same. If circuit condition is not changing, V0 is equal to dVg is always holding. So therefore, this will be again plus minus 0.8, I have to go. So minus 0.8 is 0.2 ampere. Now the current has reached 0.2 ampere and the ripple is 1 minus 0.0 is 0.2 ampere and 1 plus 0.8 is 1.8 ampere. So 1.8 ampere, let me qualitatively draw, and then this comes, right? And all the while, when this switch is on, who is conducting? Switch Q in this zone. Who is conducting in this zone? Diode D, right? Because the current in the inductor current is continuous and inductor current cannot abruptly change because energy cannot be discontinued, okay, disrupted. It has to have a smooth change. So therefore the current in the inductor will force the diode to conduct. The diode will conduct, right? But I am changing the load. External load can change. They will not have any concern. So I am now saying the R, so this is corresponding to, just now I corresponding to R is equal to 4 ohm. So this is corresponding to R is equal to 4 ohm, right? Now I change it again I change it. So what is that likely to be happening? I change it, R is equal to 8 ohm. Suppose I have felt like changing, so I have changed R. So let us go by the same method and see what is happening. Same method means I will again shift the current level. Let us take the current level is how much now? Current level is 0.5. Average current level is 0.5. So average current level is somewhere coming here, 0.5. But the ripple ideally means if I go by the same formula as V0 is equal to dVg, that should not change. Okay. So if that should not change, then what should happen? What would happen? That should not change is 0.5 is the average value, minus 0.8 is the initial value. So 5 minus 0.5 minus 0.8 is minus 0.3. So it's trying to flow a current of minus 0.3 ampere. Okay. Are you understanding what I'm saying? Is anybody having any doubt? Please tell me. And another is 5 plus 0.8 is 1.3. So it intends to flow a current of this nature and then come back to a current level of, again from there it again starts to come back to a current level of 0.3. This is what is its first intention is. First intention is that it will it will form a waveform like this, because it is following the same volt-second principle, and following the same volt-second principle, the same ripple will be there, current ripple will be there, and therefore the current would be negative. So what is the difference? The difference is the current, inductor current is trying to be negative. So let us explore, is it possible the current can be negative in this, in the first topology with diode? Can it possible? Is it possible the current to be negative? Negative current means what? Negative current means current has to flow in this direction. Positive direction is this, negative direction is this. But how can there be a negative current? Can there be a negative current through the switch? That means, can there be current through this? Yes, that can be, because the diode is there, the body diode. The problem is not with the switch, not with the switch Q, because switch is a not only body diode. This MOSFET, you know, is a majority carrier device. It has a channel, and the channel can contact current both drain to source and source to drain. It doesn't give any constraint. As long as the switch is on, the current can flow from drain to source or from source to drain. That is not an issue. So what is the issue then? Issue is that, assuming that let us take the waveform shape and consider that. Assuming that the current is initially flowing negative up to this and then positive. What does it mean? During on time, current has started like this. Then during on time, the current has reversed the direction like this. Possible. Why not? Why not? Why not? This is what I am showing here. Initially negative, started negative, then changed the direction and became positive. Okay, plus means positive. That is implied by the direction of current, actual direction of current. Initially, it started with current flowing from source to drain, then it going. Then what is happening? The current is then for some time positive, no problem. Sometime this time this is positive. So that means diode can conduct. Diode can conduct, no issue, because current is positive. Let us look, the current is positive. Positive current means this way, the green fellow. The positive is the green fellow. This current is flowing. Continuity. After you have turned off the switch, the current is flowing. But if I continue the waveform, I have to believe that current has to reverse at certain direction and flow through the diode. Flow through the diode in this manner, cathode to anode manner, which is not possible. The diode conduction in the cathode to anode manner is not possible. It would have been possible in this, because there is no this here also drain to source current flow and drain to source to drain current flow is possible. So in this case, if I look at the synchronous rectifier, the things would have been initially current would have been negative here on time, then the current would have changed to this direction, then the current would have flown in this direction in the off time of this switch, and on time of QS bar. When on time of the switch is over, on time of the Q bar is starting, and during on time the current will flow like this. Initially flow, the yellow current will flow through the source to drain. That is the path it will flow, but it will then come down to 0 and turn and become negative. That is also possible. That means this current will now flow from this to this to this direction. That is possible. Now the current will flow through drain to source. So if it is a synchronous bus rectifier, it will exactly work with our formula of V naught is equal to dVg, and the current will be like this. Current will be negative and positive. Negative to positive transition will be there in the on period, this period, dTs period, and positive to negative transition, that means here, it will be happening in 1 minus dTs period during sometime in the 1. We can calculate, but we don't have to bother at all, because our concern is that output voltage is 4 volt or not. Output voltage is 4 volt because you are giving the current a continuity. So this means here the current is always in continuous conduction mode. Current is never coming down continuous conduction mode, irrespective of the value of the load resistance. Load resistance can be anything, because the switches are such that it can take both positive and negative current, and the formula V naught is equal to dVg is always holding good. Whereas in this case, in the first case, the conventional buck converter with one active switch and a diode, we see that the current will come down to 0 and remain 0 because it cannot flow to negative. Cannot flow to negative. Then the initial value is also not right. So in a discontinuous conduction mode, let us take a page. So in the discontinuous DCM, we call it discontinuous conduction mode of inductor current. Always mentioning it with respect to inductor current, always mentioning with respect to something which stores energy, inductor current, not with respect to a diode, not with respect to a switch. There by definition will be current will be discontinuous because it is on and off. So, but the energy storage element, one of them is inductor current, and that is what is having, because capacitor voltage we cannot afford to have discontinuity, because capacitor voltage is what is the output requires, load requires, and there we cannot afford discontinuity, but we can afford discontinuity in inductor current. And as per the load, this may go into discontinuous mode, and this discontinuous mode of inductor current is stating that current cannot be negative because the diode current cannot be negative. So this current will then shape like this. Because at this point it will come to 0 and stay 0. The active switch is on here. Active switch is on for DTS. This is where Q is on. This is where the diode is on. Diode. I'll say this is diode. Diode is on. Let me not write here. Q is on, right? And then this portion, though it is off period, this is 1 minus DTS. Though it is off period, current is essentially 0. Current is in the inductor is 0. That doesn't mean the output voltage is 0. Current in the inductor reaching 0 doesn't mean that. It means that the capacitor is simply supporting the load without being helped by the inductor. That is what it means, right? So you see a third state coming in. We have 3 equivalent circuits now. First equivalent circuit is Q is on. This is the first equivalent circuit. Second is this equivalent circuit. When diode is on, this is Q on, this is D on, and third is simply inductor has no current and a capacitor is supporting the voltage. Like this. This capacitor is now completely isolated from anything. It supports this voltage, right? And this happens when load in terms of current, we think. When we say load, load and load resistance are inverse in sense. So when I'm saying load means load current. When load current is relatively low, right? And since it is relatively low, capacitor can afford to support it. It is not losing much energy. It doesn't need to support it for, first of all, it doesn't have to support for long time. And then the amount of energy required is also not substantial, because this kind of mode is coming when the load current requirement is relatively low. In the high load current requirement, it never comes, but it may come not only because of the load changes, but it may come because of the changes in the switching frequency. Even you can see that something which is in continuous conduction mode may land up into discontinuous conduction mode when you are changing the switching frequency. That can also be graphically understood. If you draw a high frequency one and a low frequency one, you can see that as the frequency is changing, if I change, we keep the load resistance same, but the frequency we try to change, then we'll see at certain point of time, because the ripple is increasing, because the delta E will be increasing. If you increase TS, that means TS increase means switching frequency reduce, then delta IL increases. So at certain point of time, you will land up into discontinuous conduction. I'll just give you a quick fill of that. Suppose it was the original thing. Suppose it was the original thing. So original thing was average current was 4 ampere, and you are going approximately like this, right? Now you increase the TS. This is the TS. So increase the TS too much. So when you increase the TS too much, what will happen? Delta IL will increase. So delta IL has increased so much that it has become more than 4 ampere. So then what will happen? It will start, it will be 0. So delta IL will be so much. Delta IL, let us say, is 4 ampere. So that means it has to start from here. I'll do the same slope. Almost same slope, and then this thing. So this is one TS and this is another TS. Then after that it will remain in 0. So you have increased the TS too much, TS2. Then you will see that the ripple being increasing so much that it will now go into discontinuous conduction mode. This is for TS low, means high frequency, and this is for TS TS high, that means low frequency. So this thing can happen with changing, even if you are not changing the load. One of the reasons it can happen is if you change the load. Another reason how it can happen is if you change the TS, because TS affects the delta IL. So therefore it can land up with that, and obviously it can happen if you change the value of the inductor. The higher the value of the inductor, it tends to go towards continuous conduction mode. Lower the value of inductor, it tends to go to the discontinuous conduction, because it clearly L affects delta IL. So this way the converter goes into a different mode called discontinuous conduction. So since it is going into discontinuous conduction mode, you see that now my analysis of volt second is now changing, because earlier the volt second was based on 2 states. Now I have to bring in the volt second based on 3 states. And earlier I was sure that if somebody the on state, the switch on state is for DTS, then the switch off state was 1 minus DTS. But now in DCM, it has a third state has come. So I have to now give new variable names to it. So I will say the diode conduction is is D2TS, for D2TS. This duration is D2TS now. That is what I will define now, right? So the remaining period is, this period is how much? 1 minus D minus D2TS. So this period is now 1 minus D minus D2 into TS. That is the duration when inductor current is 0, right? So I have to now readjust my volt second equation and find out a new formula for the conversion ratio. Earlier the conversion ratio, as you know, that V naught is equal to dVg based on 2 states of the converter, 2 switching states of the converter. Here we have 3 switching states of the converter. So 3 switching states will give me a different volt second equation, and we'll try to do that. So let me again sketch the waveform to make it more clear and to you. So this is in discontinuous conduction mode. So I should start from 0 current. So I should start from 0 current. This is D, and this is, I will not say 1 minus D, I will say D2TS. This is DTS. This is 1 minus, D2TS, and whole is TS. So remaining is, you can calculate 1 minus D minus D2TS. And the average current, what is the average current? This is the average current. Somewhere it is, somewhere this area, if you take total area and balanced by this line, that is the average current I naught, because that is always true. That is, you see the inductor is there, so average current of the inductor must be equal to the average current of the load. So that is equal to V naught by R. because capacitor on an average is drawing 0 current. So that is always true. See the circuit connections, the inductor node, there is a node consisting of the inductor and the capacitor and the resistance. So in an average sense, the capacitor is neither drawing any current or not giving any current. So its average value is 0. So average value of the inductor current is equal to average value of the load current. That is true irrespective of whether it is a continuous or a discontinuous conduction. But what is not true is the volt-second equation. So we have to write the volt-second equation again. So how do I write the volt-second equation? With the first state volt-second is same, that is Vg minus V naught into dTs. Second volt-second is minus V naught is same into, now I have taken a new parameter D2, new variable D2Ts, that is the inductor voltage. And last, what is the voltage across the inductor? Can anybody say when there is a discontinuity in the current, current is 0, what is the voltage across the inductor? In this state, what is the voltage? No, try again. In this state, what is the voltage across the inductor? That means inductor is now floating. So what is the voltage across the inductor? What is the status? This switch is on, this diode is not conducting, so that means that is also like a open situation, right? So what is the voltage across the inductor? Voltage across what is the voltage across this terminal? V naught. What is the voltage at this terminal? No current is there. So what is the voltage at this terminal? No current is there. So what? V naught. So what is the voltage across the inductor?
0.
0. So that duration is 0 into time wise, if you take 1 minus d minus d2 into ts, right? So this must be now equal to 0. So you can clearly see that now we are getting that what we are getting is Vg into d is equal to V naught into d plus d2. This is the condition of discontinuous conduction mode. So you see that immediately V naught is not V naught by Vg we cannot find out because we don't know what is d2. How do I know? I do not know what is d2. So this must be equal to d by d plus d2. So from this volt-second equation we cannot determine what will be the output voltage, or we cannot determine what is the conversion ratio. V naught by Vg is called the conversion ratio, that we cannot determine, and we cannot determine what is the output voltage because what is unknown here? Unknown is d2. So we have to find d2. So what way we can find out d2? We will apply, this is the volt-second balance condition, one of the volt-second balance condition. The second is current second balance condition for steady state analysis. The second is now we have to use the current second balance condition of the capacitor. So capacitor current second balance is saying that IC dt 0 to Ts 1 by Ts is equal to 0, which essentially means the average value of the inductor current is V naught by R. So what is the average value of the inductor current? Here we have this ripple delta IL. So I will write it as half into delta IL into duration d plus d2 into Ts, right, divided by Ts, that is the average. This is the area. Then this divided by Ts must be equal to V naught by R. Okay. So what is delta IL? What is delta IL? Let us go to next page. So what I wrote here is this one. I will almost time draw it. So, and this is the average. So what I wrote is this is V naught by R, and this is delta IL. This is DTS. This is D2TS. So what I wrote is half of delta IL. Delta IL is how much? I will take this side ripple. So what is the voltage? What is the slope here? V naught by L. I am taking minus V naught by L is the slope. So magnitude wise I am just taking V naught by L into time duration D2TS, right? This is the delta IL into total time D plus D2TS divided by TS. This is the averaging condition. So that must be equal to V naught by R, right? So V naught cancels. This doesn't come here. So I get a equation D2 into D plus D2, okay, is equal to 2L by R TS. Okay, so this you can see that this is a condition. This is a constant. This is formed by the parameters that we have chosen for the converter. So 2L by RTS is called a critical conduction parameter, or K crit. There, this is named as a coefficient of the converter. That means they have a similar impact, which I was describing earlier. I was describing that if L increases, it goes towards continuous conduction, this thing. If R decreases, it goes towards continuous conduction. If TS decreases, it goes towards continuous conduction. So they similarly affect the conduction condition of the converter. So that is why it is called a K crit or critical conduction parameter. They similarly affected. These three parameters have similar effect on the converter's conduction condition. Whether it will be in continuous conduction or discontinuous conduction is determined by these LRTS parameters, right? So this is what we are defining as K crit, critical conduction parameter, defined as. It is defined as this is this 2L by RTS is defined. So you see there is a second order equation, which is D2 square plus D2D minus K crit is equal to 0. So in order to find out D2, what I have to do is I have to find out so minus B, so minus D, it must be plus, minus cannot be, because if I take minus, both the D2 becoming negative, which is not possible practically. So minus thing I am not taking. So D square minus means 4 into K crit by 2A, that is 2, right? So D2 is now has to be solved by this kind of quadratic equation, which will be giving you the value of this for a given converter. Given converter means a converter where the inductor has been chosen, the switching period has been chosen, and the load resistance is known. So if such a thing is there, you can determine what will be the instant, what will be the duration for which the diode current will conduct. That will be dependent on so many things, dependent on the circuit conditions. It will not only depend on inductor, it will also depend on the load resistance, it will also depend on the switching period. So based on this and the duty ratio, the D2 will be determined, right? Now what do we do here? What we do here is we want to know what is the boundary situation. What is the boundary? Boundary means when the current is just on the border of continuous and discontinuous conduction, just at the border. That means this is D and this is 1 minus D. But the current is initially 0 and ending at 0. That is called the boundary condition. The border between continuous and discontinuous conduction. If the current shifts further, it will be either in the continuous conduction or in the discontinuous. One may say that this is also a continuous conduction, because precisely 0 to 0 will again give us the volt-second balance. Will again give actually two states. Actually, it is a two state, but take it as a bounded thing. So at the boundary, that means when these two things are equal, what is this? How do I define the boundary? Boundary between continuous and discontinuous conduction. How do I? What has to be D2 if it is at the boundary?
0.
No, D2 is equal to 1 minus D. D2 is defined this way. D2 is this way. This is D2. So at the boundary, so what is this? D2 is equal to 1 minus D, right? So 1 minus D, 2 into 1 minus D is equal to minus D plus I'll little bit change this. This is not critical, is at K is equal to critical. This is at the boundary. So at the boundary between CCM and DCM, K is equal to K critical. That is the critical point. So this is equal to K, I will not say K critical, this is K, 4K by K crit now. Now K crit by 2 is taken out. Is that I'm slightly confused you. I just want to define this as K, that is the conduction perimeter. Critical word I will bring in when there is a critical condition. Critical condition means when K is such a value that it has produced a boundary condition for the inductor current. That is, inductor current is at the boundary between continuous and discontinuous conduction mode. And under such a situation, whatever the value is K, that value I am defining as K crit, critical value. Okay, this K is a general value, right? It can be something to something, but K critical is pushing it to the exactly to the boundary between continuous and discontinuous. That is a new unique value, right? So that's why I am finding out now, because at the boundary between CCM DCM, this condition has to happen. D2 is to be equal to 1 minus D, and at that moment, whatever the value of K is K critical. So that is why I am writing this equation. So what I will do is I will square it. 4 minus 4 into 1 minus D square is equal to this square root. If I take, what it will be, D square plus D square plus 4 K crit. Oh, sorry, I will not do this way. 1 minute. So what I will do is I will bring it here. So 2 minus 2D. So what it is becoming is 2 minus 2D, and this D comes here. 2 minus D is equal to square root of D square plus 4 K crit. Okay. So now I square it. So 4 minus 4D plus D square is equal to D square plus 4 K crit, right? So D square cancels, 4 cancels. So K crit becomes, K crit is equal to 1 minus D, right? So this is what is equal to value of K critical. That means 2L minus RTS. K critical is nothing but 2L by RTS. So it is such a value it is reaching, 2L by RTS, this parameter is reaching such a value which is equal to 1 minus D, then it is at the boundary. So if it is less, if K is less than K critical, it will be in discontinuous conduction mode. So I write, if K is equal to 2L by RTS is less than K critical, which is equal to 1 minus D, then the converter is in DCM. Otherwise, it is in CCM, right? So if I want to have a graphical view of that, what I mean is that this is the converter. This is this is the K cret. Now this is D, converter D. This is equal to 1 minus D. This zone, this is the K critical. For every duty ratio, for this duty ratio, this is the value. For this duty ratio, this is the value. So if the converter is K value is here, then this zone will be DCM. If the converter K value is there, K is equal to nothing but 2L by RTS. That is equal to K. If this value is here, this value is nothing but this curve is nothing but 1 minus D. This is a 1 minus D. This is implying 1 minus D. So if this is here, then it will be in continuous CCM, continuous conduction mode. Understood or not? Hello? Understood, I hope.
Yes. Yes.
This is K, write it as K, okay? Because K is the generic parameter, general, 12 by RTS this value. Now this 12 by RTS value, when it reaches a value of 1 minus D, that means you say, let us say it is operating at 0.4. So in our case, what is this? In our case, it is 0.4. D is equal to 0.4. We are operating at D is equal to 0.4. So 1 minus D is equal to 0.6. So if you choose a K is equal to greater than 0.6, for example, in our case, for example, D is equal to 0.4, then 1 minus D is equal to 0.6. If 12 by RTS of the converter, right, is greater than 0.6, then it will be in CCM. So let us take some numbers. Let us take what value of inductor, it will be in CCM. So inductor for the condition of, let us say R is equal to 0.8. We had seen that R is equal to 0.8. R is equal to 8 ohm. It had gone into DCM. Now I want to push it into CCM. So what way I will do? I will change either L or TS. So let us first change L. So L has to be greater than 0.6 into R. R is equal to 8 ohm into TS is equal to 10 micro, right? Divided by 2, right? So that means it is how much? 48, 24. So it is greater than 24 microhenry. It is greater. It has to be greater than 20. Earlier we had chosen how much? I think 10 microhenry you had chosen, right? We had chosen 10 microhenry to start with. Is it? Isn't it?
Yes, sir. Yes, sir.
Yes. Yes.
Yeah. So we now see that if we want to have continuous conduction mode, even at R is equal to 8 ohm, we will need an inductor which is greater than 24 microhenry. Let us say we are keeping the inductor same. So what switching frequency we have to choose? Another way we can have, change it condition is that that I have still have 10 microhenry divided by R is 8. This is TS I have to determine, that should be greater than 0.6. So TS, that means implies that TS has to be less than 20 by 8, 20 micro by 8 into 0.6. So how much is that? (20) divided by 8 divided by 0.6. So so that is 4.16 micro. So that is that is equal to less than 4.16 micro, right? So similar way, 4.16 micro is greater than 200 kilohertz. So 4.16 micro is greater than, so some frequency level 225 kilohertz will again push it back into continuous conduction mode, right? So in the continuous conduction mode, we have seen how this thing can be obtained, and so now you will see that continuous conduction mode, the voltage ripple expression is slightly complicated. Slightly, I will sketch the waveform and tell you to determine it. I will not do it now. So what is the approach we will take? Anytime we have to find out voltage ripple, we have to first sketch the capacitor current, because that is what is the cause. C dV by dt is IC. Always remember the first equation. Current ripple, you always look for an expression L V is equal to L di by dt. So that is where, from where you will get the delta L. C dV by dt is equal to IC, from where you will get the capacitor voltage ripple. So that means that we have to find out the capacitor current waveform in the discontinuous conduction mode. Let us see if I can sketch the capacitor current waveform in the discontinuous conduction mode. So let's say this was the waveform. This was the current, and it was coming down to 0 here, and it remained 0 here, right? So this is the delta IL, which now we know, because we know D2. We can find out. By the way, you remember that V0 was what expression? V0 was D by D plus D2 into Vg, and D2 expression we have found out from here. D2 we have found out from D2 is found out from here. This is how D2 is found out. So by putting these values, you can get a value of D2, right? So in our case, let us compute once D2. Once let us say D2 was how much? With 10 micro, how much is D2? D2 is minus D plus square root of D square plus 4k by 2. So what is this? Minus D minus 0.4 plus 0.4 square plus 4 into k. How much was our k? K is equal to 2 into 10 micro by RTS. R is 8 ohm into TS. TS is also 10 micro. So it is equal to 1 by 4. So it is 0.25. 0.25 by 2. So how much is that? Minus 0.4 plus square root of 0.4 square plus 4 into 1. So 1.16 square root by 2. So how much is it? So it is coming out to be 0.334 approximately. This is equal to coming out to be our D2. This is what is D2. So what will be the output voltage here? Output voltage V0 is equal to how much we said? D, 0.4 divided by D plus D2, 0.4 plus 0.34 into Vg. Vg is equal to 10. So in a discontinuous conduction mode, the actual voltage increases compared to what it would have been for continuous conduction. That you can see obviously from the expression d by d2. D by d2 is the expression, right? This expression, if we look at it, and d2 is always less than 1 minus d. So this is increasing. So V0 is increasing compared to CCM, compared to CCM, because d2 is less than 1 minus d. Because of that, it is increasing. So here how much it is? 0.4 into 10, 0.4 into 10 divided by 0.4 plus 0.34. So it is 5.405. You can see that it is not 4 volt anymore. It under discontinuous conduction mode, the output voltage has increased. So any converter, if whatever you are expecting from the continuous conduction mode, you get output voltage more than that, then you know that the converter has gone into discontinuous conduction mode. So here you can find out delta IL now. Delta IL will be how much? V0 by L, in this case, V0 is 5.4 by L is 10 micro into D2 TS. D2 also we have found out 0.34 into 10, right? 10 cancels. So delta IL is 5.4 into 0.34. So it is 1.836 ampere. That is delta IL, right? So this is the this thing, and I0 is how much? I0 is how much? I0 is equal to V0 by R. V0 is 5.4 divided by 8. So it is how much? 0.675 amperes. That is ampere. This is the instantaneous current waveform. This is the average value of the waveform. So the current, now you see how difficult it is. How difficult it is to find delta V0. Maybe this can be given as an assignment. This is the zone when the current is positive, and it is cutting it here and here. So you have to find out these two times, T1 and T2, maybe T2. So because it is conducting between T1 and T2, this is the positive current, will give you the ripple. The ripple will be wherever it is, initial value wherever it is, it will increase here. It will increase. It will have a ripple which is increasing. This is the delta V0. This is the delta V0 now. So you have to calculate. So what you have to do, you have to find out. It is easy, simple geometry. You have to find out what is T1, intersection between the slope of the current and the value of 0.675. This point current is 0.675, where it is intersecting and what time it is intersecting. This being greater than the average value, that means capacitor is charging, right? I ignore this part because I know that in this part it is only decreasing. My job is only to find out delta V0. That means over minimum to the difference between the minimum voltage to maximum voltage. And I know the voltage is minimum here and the voltage is maximum here, because this time is positive, so it must be increasing, right? So from that argument, if I find out T1 and T2, I will be able to find out what will be the delta V0 or the ripple of the converter. Please compute it, and then in the next class, you please tell me how much is this value of delta V0. Is there any doubt in the way this has to be done? I am not doing anything different. I am doing the same basic principles. The basic principles is volt second balance and current second balance. Only thing is that this current second balance equation is synonymous with voltage voltage equation in a continuous conduction mode. But in the discontinuous conduction mode, you need to find them independently, because you need to find one extra variable. In continuous conduction mode, you have only one variable d. But now in the solution, you have to find out what is d2 as well. Without d2, we cannot find out v0. So therefore, you have to have second equation, two equations, two unknowns. So therefore, you have unknown equation v0, you have unknown equation of d2. So therefore, you have to apply two equations, use two equations. One equation is volt-second balance of the inductor, and the second equation is the current second balance of the system. So after you find out v0, in exactly the same way you can find out delta IL. Exactly, delta IL is the slope into time. So that way you can find out the delta IL. After you have found out the delta IL, you have to find out what is the value of I0. I0 is V0 by R, right? So V0 by R, sorry, I0 is V0 by R. V0 you have found out earlier by formula of d by d plus d2 into Vg. This has given you V0. And then you need to find out how much direction this current, the capacitor current, this is the capacitor current, IC, exact waveform of the capacitor current, for how much direction capacitor current is above I0. And that is the duration when the voltage ripple will be coming. Any converter, your approach will be same. Your approach will not be different. I want you to do one homework and tell me this one. I take a converter like this and tell me what will be the voltage ripple in this case. This converter is called multi-phase converter. This converter is called multi-phase buck converter. Multi-phase converter. Some similar with three-phase type of thing is there. So how can we bring the same idea here? We can bring the same idea there by doing this. This is the basic source, but I am splitting it into two phases. The buck converter, I am splitting it into two phases in the input side and then combining them at the output side. So splitting into two phases means this. This is one buck converter, you already know. This is one buck converter, one inductor, one capacitor. Then I draw another buck converter. Let me say draw it in this from the same source. So from the same source, I draw, same source means I'm still tapping from here. But there is a difference. This is still tapping from here. What I'm doing is I'm splitting the power between the whatever the total power. Total current is getting split into two parts, Ig1 and Ig2. Ig2 and here Ig1. Two parts I'm splitting. And then I combine them at the capacitor. I'm not doing any capacitor, sorry, I will wipe off this capacitor. There is no extra capacitor, and I am combining them at the output, right? These values are all equal, same switches. So splitting the power. Suppose you have to do a very big buck converter and you don't have appropriate switch with the current rating, etc. So you are using two units, two identical units, almost identical units, and then at the capacitor end you are combining. So let us say 500 watt buck converter you have to do. So you have distributed the power into two 250 watt converters. 250 watt converters. Now what is interesting here is, that is okay, that is almost commonsensical. What is interesting is how do we apply switching pulses to them? We apply switching pulses. Let us take the similar kind of expression thing, how 10 volt, 4 volt kind of thing. So there our pulse was like this, right? This is maybe 0.4, and then whatever, and then other one is this. I am talking about continuous conduction mode. I am talking about continuous conduction mode. Let us understand in continuous conduction. So how about the 50% is here, right? It is like a two-phase converter, two-phase buck converter. So if this is two-phase buck converter, the entire period can be conceptually thought of as 360 degree. Right? Period is 360 degree. That is the concept. And this half period is therefore 180 degree, or corresponding to a duty ratio of 0.5 D as such D. This is operating with a time period of DTS. One of them. The other one is doing the same identical thing, but it is phase shifted by 180 degree, or corresponding to a duty ratio of 0.8. So what it is doing is, it is having a current waveform like this. Like this. So this is this is IL1 and this is IL2. All of them having the same inductor. Inductor value is not different, identical. All the component ratings, everything is identical. Switching pulse is also identical. The same duty ratio DTS will be applied here. This is also DTS. This is also DTS. Same duty ratio. The overall period is called TS. However, there is a phase shift. This is a phase shift of 180 degree for two phase. If it were three phase, the phase shift will be 120 degree. If it were four phase, phase shift will be 90 degree. What is the advantage? What is the advantage of that? The advantage that I want you to find out is in the voltage ripple in the capacitor. This capacitor delta V naught will be changing. Why? You please sketch the current at the summation end, at this end, after summation, that means you add IL1 plus IL2, sketch IL1, IL2 and sketch IC and find out what is, IL1 plus IL2 is equal to, if I can call it IL, and IC and V naught by R. Can you tell me quickly how much is V naught by V naught? It is in continuous conduction mode. How much is V naught? I am saying duty ratio is 0.4. Vg is equal to 10 volt. V naught is equal to how much? This du is equal to D is equal to 0.4. So how much is V naught? V naught is still 4 volt. This is still 4 volt. Okay, this is still 4 volt. Only thing that has happened is this current has increased. The current is now corresponding to average of IL1 plus IL2 average. Okay, so I want you to determine what is determined, and V naught is equal to just now equal to 4 divided by R, whatever the R is. Okay, let us say R is equal to, I am putting R is equal to, earlier was 1 ohm, I have put R is equal to 0.5 ohm. Let us say R is equal to 0.5 ohm. So this is equal to 8 ampere. I am just trying to make it this thing. The numbers are all equal. L is equal to 10 micro. TS is equal to 10 micro. This is 10 microfarad. This is 10 microsecond. Find delta V naught. Okay. See, you take the value whatever was there. I don't remember. 25 micro was probably the value. 25 microfarad. Find delta V naught and compare it if there were no phase shift. If there is no phase shift, both of them are switched at the same instant without any phase shift, then what would have been the delta V naught? Okay, if there is phase shifted converter and not phase shifted converter, what is the difference? Please find out. Compare delta V naught with respect to no phase shift. No phase shift. There are still two converters, but you don't give this 180 degree phase shift. So compare the delta V naught, what will happen with respect to that situation. So let me stop here.